Big data is both massive and messy. First, let's do a little bit of review. The IPython notebook saves automatically, but we can click on this save icon if we want to do it manually. That creates a checkpoint. You can do the same thing through the file menu and revert to a previous one if necessary. You can edit cells of all types using the edit menu. You can run a code cell. There's interrupt and restart from the kernel menu, and a list of keyboard shortcuts that you'll probably get used to. They're very useful. You can also show YouTube videos, but notice when we execute the YouTube video, it's too large. So we can click one time and make it into a scrolled output. Double click hides it all together and gives us a bar we can click on to bring it back. Notice the 5 means that we've already executed network X, so if we hit the tab key, that will bring the entire word network X up, put a period, and we'll see all the methods and things attached to the network X namespace, including graph, which we'll use later. And this is a tooltip. We can make it bigger by clicking on plus. We can scroll down, see the different things we can do, including some examples. Clicking on the caret will actually bring up a pager, which is at the bottom of the page. You can detach it with this icon, or you can hide it again by clicking on the X. And let's look at some other things. If you put a question mark in front of a Python, you'll get a pager as the help. If you put a parentheses and hit tab, then once again you have the tooltip that you can either make into a pager or make larger. And again, you've got examples. Notice that the notebook is saving automatically. Notice that we're going to type and create an error situation. We haven't closed the square bracket, so this end parenthesis is red. However, when we finish the square bracket, both are green because they're paired, and now both parentheses are green because they're paired. And now we've executed it. Now let's look at some magics. All the magics are given by the lsmagic command, including the who magics, which I like quite a bit. Who_ls is a list of things that have been defined so far, names and the things attached to them. If you want to see what kind of things are attached, you can hit whos. And this will actually bring up a table of the names and things that you can see. Finally, notice that if you have a really large view and you need to scroll past it, you probably will need to go to one side or the other. There's an internal scroll bar that is only used for the actual cell itself. Now let's get back to looking at big data being massive and messy. Let's review a bit. The 3 V's, this was actually a term that was introduced by a group called Gartner, which is a major player in the analysis of big data. So the key is that big data is massive, messy, plagued with missing data, and cursed. So how do you deal with the 3 V's and the consequences of it? Well, dimensionality and complexity are key. Big data is large and complex, but it's not necessarily random. For example, the Library of Congress is big data. Huge numbers, huge varieties of documents. But it's not random, not even a little bit. So when we see that answers are not obvious, it's often due to the large variety of information within the data rather than the randomness or random effects hiding the answers. Networks are a way of dealing with this mess. That's why we use networks so often. And again, the mess doesn't necessarily come from randomness, often doesn't come from randomness. So what we want is to construct networks that best handle the messiness within the massive. So the messiness in the subeconomy problem has an obvious source. If you look at the data, you'll see that some of the transactions are relatively small, less than $100 a month. So, Mr. Smith may stop a couple of days a week and get a gallon of milk or a loaf of bread. So these things are small relative to what's going on, and so that means we want to pre-process the data. So pre-processing helps deal with messiness, but there's a huge caution. When you pre-process a data set, you actually change the data set. And you can actually get predictions based on how you pre-process rather than what the data actually says. So what we're going to do in pre-processing the sub-economy data is we're going to set to 0 all monthly transactions that have a sufficiently small magnitude. We're going to start small because we always want to be aware that pre-processing could corrupt the data and give us misleading predictions. So we're going to start small, and then we're going to change things only by small increments. So here's an example. Going back to our IPython notebook, here's our data. Notice there are the small values, 60 a month, 50 a month, 30 a month. And again, I'm not going to narrate this because it is in the notebook, but we're going to define a thresholding function, and initially any values between -10 and 0 inclusive, it's going to set those to 0. So threshold of -10 is 0, threshold of -70 leaves it the same. Then we're going to apply map, the threshold function, and that's going to make 0 anything that's $10 or less. Now, as you might suspect, because we did so little pre-processing, we're not going to make much change, if any, in the results that we got before. So notice here are our sub-economies, and if you went back and checked, I think this is exactly the same result that we got before. That's good. That means our pre-processing, initial pre-processing, was mild enough. Now we increment by 10, so now if it's $20, -20 up to 0 spent each month, that's going to be set to 0. And we go down through there again. And of course the question is, well, how far do we go? Well, every big data problem is unique. How much pre-processing, how much representation, how much you weight vertices versus construct graphs, these are all questions that have to be figured out for each problem. And the key is you need to go incrementally. So now we're going to change the threshold to -30. And notice it still doesn't change the 70. Notice it did change that Anderson was spending $30 a month at Thrifty Foods. That's now been thresholded to 0. Anderson and Thompson, this is from previously. This is from the original data. And you'll notice that both Anderson and Thompson were at 30, and now that's been set to 0. Thompson's also 0. So now with this thresholding, which we can see from our small view of this data, it does change the data. And notice it also changes the results. But not for the better. Now we have even more small sub-economies. So we're just going to keep thresholding. We just keep plowing down through here. This is very typical of what we're going to be doing this semester with Python, because each big data problem is unique. Notice the results change slightly. Because each big data problem is unique, we each get different assignments. As a matter of fact, here is the assignment 1 based on my username. It's unique to me. Let's see, okay. So it's unique to me. What I want to do is I want to show you that actually there is a command called grade. And I can submit my current list of sub-economies, and that actually tells me how well I'm doing. Not doing so great right now. Okay, so let's change it to 50. Run it again. Now we're getting some larger. So now our largest sub-economy is up to 21. And I've actually contrived this assignment and this example so that there's only one very large subeconomy once you get enough thresholding. Notice we're up to 29%, so I've got a 29 on my assignment now. So now we go to 60. And it's also set up if you do too much thresholding, of course, then you destroy the original data, so we also detect that in the grading, whether or not you're doing too much thresholding by producing a subeconomy that's too large or not quite there. So I changed it to, what was it, 60, and I'm getting there. Notice the is example equals true. You'll remove that for your assignment. So this is set up to grade the example, not the actual assignment. So now let's go to a threshold of -70. And notice now everything $70 to 0. And notice now we only have one subeconomy. And we ask the question, is this the subeconomy that's predicted by the least amount of thresholding? So we grade it. Hey, got it. The grading mechanism gives you some feedback, and hopefully this will be helpful in doing your assignment. But one of the things we see is every big data problem tends to be unique. What works well on one problem may not work at all with another. And representations, graph theoretic or otherwise, you could get either fast or slow, i.e. centuries to run algorithms. So let's look at the subeconomy problem a different way. It turns out that our criteria function defines a transitive relation. In other words, if k of xy is true and k of yz is true, then that means that x and y and z both form subeconomies, and therefore k of xz is true. So every household in a subeconomy is connected to every other. So a subeconomy is what's called a clique, a subgraph of a larger graph, which there's an edge between any two vertices in the subgraph. So we could have approached this as a maximum clique problem. So the subeconomy problem could have been find the largest maximum clique. But there's a theorem that says the largest maximum clique is NP complete. This in essence says that the best algorithm is just check every possible subgraph, or at least the best algorithm that we know now that's equivalent to all the other ones. And this is the algorithm, of course, that would take 10 to the 52nd years. However, we're going to see later on that there are times when finding a maximum clique is feasible. So just because it's NP complete in general doesn't mean it's not a good method. It can be used effectively. So every big data problem tends to be unique. And every big data problem has a complex underlying structure, and the structure tends to be what defines how you approach the problem.